Okay, so well, happy week 1 Friday, you guys, and today's also a Data Fest day, so I'm hoping to see you guys there. I'll come by this evening and probably stop by tomorrow as well. But anyway, we got to talk. I guess we got to cover today's lecture. Let me try opening it here, and we'll try this. Okay. All right. So here we are, lecture 1.3. So last time we left off and we did the matrix notation derivation of the least squares estimate, right? So we went through, did a little bit of vector calculus, and we found the way to estimate our parameters W, okay, with the matrix W hat. And now we'll take a look at maybe getting a nonlinear response from a linear model, okay? So a linear model just means that we are combining terms in a linear fashion, you know, W1 times this variable, W2 times this variable, W3 times another variable, that's what we'll do. We'll take a look at the Olympic 100-meter race time data once again, okay? And this is what it looks like. And what we're going to do is, on Wednesday, we had our X matrix, which was a column of ones and the column of X values. And what I'm going to do here now is I'm going to add in another column, which will just be X squared values, okay? So now we can have a linear and a quadratic response. So we're going to just expand our X matrix by adding a column for X squared. So this is your first observation, W, X1, X1 squared, I'm sorry, 1, X2, and X2 squared, so on and so forth for all n observations, okay? For those of you who are arriving a little bit late, I have an online poll going for attendance, and you'll just go to, you know, onlinepoll.ucla to respond to that. So just go ahead and get your attendance put in. Okay, and so this is what we have, and this is how we might construct such a matrix in R. Okay, so I'm going to take the X variable, which is the year in the Olympic data set. I'm going to extract that out. Olympic $year I assign to little x, and then I'm going to just use cbind to bind a column of ones, x, and x squared, okay? And so here's my matrix X, and I decide to just rename it to 1, x, and x squared, and we can see we have a column of ones, the year 1896, and when you take the year 1896 and you square that, you get 3,594,816, okay? And so on and so forth. With the year 1900 squared, you get 3,610,000, so on and so forth. This is what our X matrix looks like. We have a total of 28 observations, so X is 28 by 3, 28 rows, 3 columns, okay? Our predicted values are W0 plus W1 times xn plus W2 times xn squared, okay? Which can still be written in matrix notation as W transpose X, okay? The vector W transpose times the vector X, okay? And this is exactly what we had when we were dealing with a linear model of one variable, when it was just the column of ones and the column of x's, okay? And so, you know, using the same thing, the column of predicted values is just going to be xw, exactly as it was before, right? So xw, so we now have n by 3 multiplied by 3 by 1, and so we're going to have a n by 1 matrix over here, okay? So XW is a kind of a column matrix or a vector of n values, and it's just the predictions for our observations when we apply, you know, kind of our three coefficients, W0, W1, and W2. So far, so good. All we've done is we've just added a column to the X matrix, and we're adding one more parameter to our, I guess, our W vector of weights or coefficients for the linear model. Okay? And so because the predicted value is exactly as it was before, then our loss function is also exactly what it was before. Okay? So here, our loss function, the mean squared error, is still t minus xw transpose times t minus xw. So this is exactly how it was before. You can check back to Wednesday's notes, and you can see that, you know, if we take this column and we multiply it by its transpose, you're going to get exactly what we're talking about, the total squared error, and then we divide by n. So this is going to be the mean squared error here. This is our loss function. And so this is exactly what we saw on Wednesday. So I don't have to go through the same exact derivation again. But because this is exactly the same, this means the W hat that minimizes this loss function is exactly what we had on Wednesday as well. Okay? All we've done, the only difference, so this is exactly the same. The only difference between today and Wednesday is the dimensions of x. Okay, so on Wednesday, x was n by 2. You had n rows, the number of observations, and 2 columns, a column of 1s and the column of x's. Today, x is n by 3. You have n rows, for, 1 for each observation, a column of 1s, a column of x's, and a column of x squareds. Okay, so that's what we have. This is, so just the dimensions of x has changed. And so when you multiply this out, W hat is going to be a 3 by 1. Will be dimensions 3 by 1. Okay. Is that all right? That I've just kind of gone straight from here, straight to here, saying that because this is exactly what it was, this was on Wednesday, we're going to get the exact same result today. Okay. Yes, question.
Slide 7, there's W transpose x.
Yes. It should be. So W is, W by itself is 3 by 1. Okay, so transpose is going to be 1 by 3. And if we take xn all by itself, xn is 3 by 1. Okay, so remember, the matrix X is each xn transpose. So x by itself is a column that's 3 by 1. So this is going to be W transpose is 1 by 3, and xn is 3 by 1, so this will be a 1 by 1 scalar value. Okay, and then yeah, so x, when we take every observation and we transpose them and combine them, we're going to have an n by 3 matrix. Yes?
Isn't the matrix n convention row by column?
Yes, the number of rows times the number by the number of columns.
So 3 by 1 would be 3 rows and 1 column.
Correct. So xn is 3 rows, 1 column. And x is each observation transpose to become. So here, let me go just quickly go back to Wednesday's lecture. So so x looks like this. Xn looks like this. Okay, so now we just have 3 values in it, 3 by 1 rather than 2 by 1. And then our X matrix is each of those things transpose, so it becomes this. Is that okay? All right. Okay, so we're here. The loss function, this formatting is going to be exactly the same, and therefore when you go through the matrix or the vector calculus to solve for the minimum, you're going to find that the W that minimizes this function is going to be X transpose X inverse X transpose T. Okay, so So again, we're dealing with the Olympics data, okay? And so I have my matrix X. I have my matrix X, and so I can just go and say, all right, let's do X transpose X inverse. So we throw that into solve, right? So X transpose X is what we have here. So you do transpose of X times X, and then to invert that, you do solve. That's R's way of finding a matrix inverse. Okay, and then we multiply that by X transpose times the response T, but we throw it into a matrix to make sure that, that it becomes a matrix, okay? However, what we can see is that when I run this, I get an error. It says, error in solve default, system is computationally singular, blah, 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 okay? The issue here, okay, it's not that I've done anything wrong, okay? The issue here is that when I do X transpose X, when I do this matrix, because I've got huge numbers here on the order of, 3 million, 4 million, when you do an X transpose X, which is effectively like a squaring operation, you're taking a matrix and you're multiplying it by itself, but you do it in such a way that the dimensions align, you're basically doing a squaring operation. And so when you multiply something on the order of 4 million times 4 million or whatever, and you sum these things up, now we're getting onto the order of 10 to the 14th power, okay? And I don't know if you remember how to take the inverse of a 3 by 3 matrix, but it requires calculating the determinant and all sorts of stuff. And basically the issue is that because this number is so huge, it creates issues in our floating point arithmetic system, okay? Because floating point arithmetic loses certain precision after, it can only show a certain amount of precision, so we run into problems, and that's basically the issue, okay? And so it gets, R detects that, you're going to get a value that's smaller than the machine epsilon, which is on the order of 10 to the minus 16, and it's going to throw an error because of the computational instability. It recognizes that things are no longer be accurate. So it's going to say that it can't find the inverse of this matrix, and it says there's an error. But that's not true. The inverse of the matrix does exist, okay? So one cheat that we can do is we just, when we create our X matrix, I just multiply the X squared value by 0.0001, okay? And so that brings it down to something smaller, okay? And then I can calculate the inverse in it, and it doesn't give me an issue, okay? So just by saying I don't want to deal with values in the millions, but values in the hundreds or something, just dividing it by, say, 10,000 here, fixes the issue, okay? I'm doing the exact same operation that I had before, X transpose X inverse, okay? I've renamed my matrix to be X SC for X scaled, okay? So I can still do X transpose X, and now I can inverse this, okay? I can do solve, and it doesn't throw an error. I can multiply that by X transpose and multiply that by our T, and we get our W hat matrix, okay? And so this will be the coefficients to use that will give us the least squares estimate here. Okay. So this is what we have using just matrix operations, right? And I can just kind of compare this and say, well, what if I wanted to use R's LM function, okay? So in general, we're doing all of this stuff with matrix operations, which is fine and great. But in general, LM in the computer has been optimized for high performance. So I could just say, let's fit a linear model where we're going to predict the time column in Olympic based on our X matrix. All right. I have to throw in a 0 plus. And you guys, do you remember doing anything like that? Okay. The 0 plus. So by default, linear model will the LM function in R will fit an intercept term, okay, by default. So you can just do y tilde x, and it will fit x plus a an intercept, a coefficient, okay? But that's already handled inside our X scaled matrix, okay? Our X matrix already has a column of 1s for the intercept term, and so we don't want to fit a separate intercept term, okay? If we fit a separate intercept term, we're gonna, well, it's not gonna throw an error, but you'll get, it will say it can't figure something out for that thing, okay? So, so we throw in a 0 plus, and that tells LM not to fit an intercept term. Yeah?
What if you did y tilde x plus x squared? It won't return an error. It'll still give you betas, right?
Yeah. If you did yeah, y tilde x plus x squared, it will.
It isn't scaled, so there is an underlying.
No, you know, it'll. LM is well designed, and it can handle the really big numbers. It's just the inverting of this matrix is not optimized for these huge numbers type of thing. Okay, but LM is, and LM doesn't do matrix inverse operations. It figures out the values some other way. Okay, but yeah, so you could do time as explained by x and x squared, but because it's not scaled, you're going to get different things. So I did it using this matrix to just show that these values, 396, negative 0.38, and 0.944, are exactly what matches what LM fits when we fit it I don't know, maybe the way we're accustomed to. Okay, so so I guess all this to show that saying that W hat follows this same formula that we found on Wednesday still works by kind of showing that the computer matches in these two ways here. Okay. If you want to, so now that we have W hat, which is this 3×1 matrix, if we want to make predictions, or if we want to just see what the fitted values are, we just take our X matrix and we multiply it by W hat. Okay. So the predicted values, again earlier, I guess I'll go back to this one. So the predicted values can just be written as Wx or x times W when you're dealing with the entire matrix. So the predicted values are xW and so that's all we're going to do here. We're just doing x times W to get the predicted values T hat. So this is our vector of predicted values for each x observation we have. We're going to have a total of 28 of them because that's how many rows we have in our X matrix. And then I can plot that, right? So here's my data, year by year on the x-axis, time on the y-axis. And then, so we've got our points, and then I'm going to just add a line for the year and our predicted values, T hat, okay? And so we can see we have a quadratic fit right there. Okay, so far so good? Okay, so I created that column in our x squared thing by taking 1 and then taking x and I'm squaring it myself, okay? That's fine, okay? And we handled the computational issue by just scaling them down, shrinking them a little bit, okay? R actually has a function called poly, okay? And I'm not sure if you guys have used this, but what poly does is it will take, some column of values and it will return, it's squared and cubed and, whatever order you want, okay? But a nice thing about the poly function is it does it in such a way so that the resulting matrix will have columns that are uncorrelated, okay? And what that means is that if you think about, if I just took the numbers like 1 through 10, and I squared them, and I cubed them, and I raised them to the 4th power, you're going to have highly correlated values, okay? Because as x goes from 1 to 10, x squared also increases. Big values of x are associated with big values of x squared, and big values of x cubed and big values of x to the fourth, and then small values of x are associated with small values of x squared, x cubed, and x to the fourth. And so you're going to have a high correlation, and one of the things we learn is that if your variables are highly correlated, it can produce some instability in the estimates. And so what poly does is I don't know if I can just kind of draw this, is it kind of shifts the, so if I just take, let's say x looks like this, right? And if I did x squared, it would look like this, and x to the third would look like this, and x to the fourth would look like this, right? What poly does, so this is just kind of the manual power x and x squared and x cubed and x to the fourth. What poly does is it does something like this, and then it recenters where the quadratic thing goes, and it does something like this, and it will fit these things so that the resulting polynomials are uncorrelated, okay? So that we can't say large values of x are associated with large or small values of the second order or the third order or the fourth order polynomial, okay? So it decorrelates them. It still maintains, however, whether that there is a relationship with the linear, the quadratic, cubic, or fourth order polynomial. Okay, but anyway, here I'm just creating a matrix called x poly, and I'm binding a column of ones with poly x2, and what this will do is it creates two columns, and then here's the head of this matrix. And again, I can do the same kind of thing. I can use LM to fit this, and I get these coefficients, 10, minus 2.5, and 0.54. And I could also do the matrix operations x transpose x inverse x transpose t, but I'm just kind of skipping that right now. And then so I fit the linear model. I ask for the fitted values, and then we can plot them. And I'm just going to go ahead and I'm going to just say, let's try fitting a third order, fourth order, fifth order, and sixth order polynomial. Yeah, question?
How do you know what those coefficients mean?
How do we even know what these coefficients mean? Yeah, now we lose a lot of the interpretability in as far as the direct meaning of the coefficient itself. Okay. However, if we find that there is a relationship with the x squared term, we can say that there is somewhere some kind of relationship with we can say there is a second order relationship, even though the coefficient all by itself has lost a little bit of meaning on its own. Okay, so we can say, and it could be, we could talk about there being a second order relationship to time, but if we think about it, it's very unlikely that we can take our, let's say there is a second order relationship with time for race speeds, okay? But what we won't be able to say is that, oh, we just take our year and then we square it and we multiply by some number. Because that in of itself, if we think about it, doesn't have a whole lot of meaning either. Because the year today is 2019, but 2019 has been, why is it 2019? The number 2019 is kind of this arbitrary, the zero is set a little bit arbitrarily, based on historical events and, of religious significance and things. But, here we are in 2019, and is there inherent meaning to the number 2019? And in the computer, the zero date is 1970, okay? And we're measuring time based on, where we are versus 1970 and things like that. It's all we can say is that there is a second order relationship with time, but the actual value itself is a little bit strange, right? And so, you know, even things like temperature, we're accustomed to, you know, Celsius maybe being kind of, but Fahrenheit, you know, the 0 points on these things are a little bit arbitrary, okay? Only when you're dealing with Kelvin does it actually kind of make sense. So yeah, you know, you lose a little bit on the direct interpretation of the coefficient, but it's still significant to say there's a second order relationship. Okay, so anyway, I'm gonna go ahead and I'm gonna just fit a whole bunch of different linear models based on polynomials, and here I'm getting rid of the 0 plus because I'm not gonna bother creating the matrix itself, but I'm gonna just have it fit the result of what poly spits out, and that will also fit in a coefficient. And then, so based on all of these things, I can plot a whole bunch of lines, okay? So this first line plots the data, and then each of these following lines takes each model and their fitted values. And we're gonna just add a line in different colors, red, orange, green, blue, purple, and dark gray. And these are the different fits that we get. So to our data, we can see the linear model in red, the straight line, and then, and it kind of hurts my eyes to stare at all of these, although it's a little bit pretty. It's like, I don't know, a rainbow ponytail here, but you know, we can see that the higher order polynomials get a little bit closer to this extreme value out here, okay, where the races were recorded in just straight seconds because that was our most accurate measure of time in 1896. And you know, I don't even know how stopwatches worked in 1896, but that's what they had. And anyway, as it has, we can see this kind of downward trend here. Okay. And then, and if you had to look at these, and then in kind of your classical approach, we had said, okay, well, which one's the best model, right? We'd say, is the, should I use the quadratic fit, or the third order, or fourth order, or fifth order, or sixth order polynomial? You might use something like this, okay? And you would ask for the summary, and you would look at, you would just kind of look for the stars, right? And if you see the star, it's like, okay, let's keep that term. And then over here, you don't see the stars here, like, okay, we'll go up to, you know, here's the fit on the sixth order polynomial, and then the stars run out around here. So I don't know, we kind of just say, all right, let's get rid of these terms or something like that. Or, you know, maybe it requires a little bit more thinking than that. Okay, does it make sense that time has this quadratic or cubic relationship with time, or the year that that the race took place? You know, what, you know, and I don't even know what it means for that the race time has a third order relationship with the year or the time in which the event took place. That's hard for me to comprehend and conceptualize what that means. And so one method that we kind of lean upon is this idea of cross-validation, okay? So cross-validation removes the need to have to think very critically about the implications of these relationships, and rather we just evaluate the model based on its predictive performance, okay? So rather than having to say, well, does it make sense to include this variable, and I'm not quite sure what it means to have a second or third order relationship, you know, with time or money or whatever it is that we're talking about, we can just say, well, how well does this model predict other values, okay? And so this kind of brings in the idea of training versus testing, okay? And in cross-validation, we split them things into, we take all the data that we have and we will split it into a training and a validation set, okay? So in our Olympics data set, we've got 28 observations across kind of, you know, a little over a century of Olympic events, we've got 28 observations, and we break that into training and validation, okay? And what we do is we fit a model on the training data, all right? And so, you know, for linear regression, it just means finding the estimates W hat, okay, for linear models. And then after we fit that model and we have our current W hat, we say, well, how would this model predict the values in the validation set, okay? So the validation set was not used during the training. So the parameters that we estimate in training have no idea about what exists in this validation set. And so we say, well, how well did these predict the values in the validation set? And we use some kind of measure to measure its performance, some kind of metric. So often we use mean squared error. There's other ones you can use. And then we compare these metrics to kind of choose the best performing model, okay? So I'll start off with leave one out cross-validation, okay? Leave one out cross-validation says when we split our observed data into a training and validation set, basically just one observation is going to be the validation set, okay? And everything else will be the training set. So we fit the model on everything but one data point, and then we'll say, how well does this model predict the one data point that we left out, okay? So we leave one out, and we say, okay, we're going to fit the model on this. How well does it predict the one we left out, okay? And so every observation in your data set will have a turn at being the validation point, okay? So the first one, you know, you leave out one of them, and then you try another model, and you leave out a different one. And you go through, and if you have n observations, you're going to fit n different models, and you're going to validate it against the, that one observation, okay? So to kind of demonstrate this, I'm going to just do a very small data set, a toy data set with 4 observations, okay? X is 1, 2, 3, 4, and our predicted values are 1, 3, 2, 4, okay? So this is what it looks like. 1, 2, 3, 4, and 1, 3, 2, 4. And if you fit a linear model on all 4 points, it would look like this, okay? But this is what it means for us to have kind of the training and validation. Here I'm going to say I set my index to 1, 2, 3, which means the validation will be observation 4, okay? And I start off and I initialize kind of the total squared error to kind of keep track of how this model performs with a 0. So I say my training X is I'm going to subset X to the values 1, 2, 3, and the training T I also subset to just take the first 3 observations. And then the validation points will be everything that's not in the training. So I do minus the index, and validation T is everything that's not in the training minus the index, T minus the index there. All right, is that okay? And then I combine these together to make a data frame. I'll say X is the training X and T is the training T. And then we're going to fit model, leave one out, which will be a linear model on T, predict T based on X, and the data we're using is the training data. Right? Okay, so this is if we fit on all 4, and if I just keep the first 3 observations, so I throw this one away and I fit a linear model, this is going to be the linear model that it fits on these 3. Okay, and then and this is the one validation point. All right, so we can see that when we have all 4, it does a better job of predicting the validation point, right? But here I only have these 3, and I'm fitting a model on these 3. Here's the validation point, and we measure its distance from its prediction, and we square that, okay? And it turns out the squared error is exactly 1 in this case. All right, and the next one, we're going to before I get ahead of myself, we're going to ask the model to make a prediction based on the validation point, and we take the difference between the validation point, the actual value, the validation point, and its prediction, and we square it, and we'll add that into the total squared error. So we're going to just keep track of its thing. So right now, after one thing, our total squared error is going to be 0 plus 1, so it's a total of 1 right now. Okay, and we go through and we do this for all of the other ones. So again, here's all of the data points and the linear model, linear fit on all 4 data points. This time, so the first time we threw away this one, this time we're going to throw this data point away. We're going to hide this one. Okay, and if we fit the model on the remaining 3, this is going to be the model that gets predicted. Okay, we add the validation point back in, and we say, how well does this model that was fit on the other 3 predict this? Okay, and we get a squared error of 1.65. Okay, and then we'll add that to our total squared error. We'll go through and we do the same thing. Here's all 4 data points. We're going to throw this one away. We're going to hide that one. Okay, and when we get rid of that one, the model that gets fit looks like this. We say, how well does it predict that data point that we hid? Okay. And it has a squared error of 1.65. Okay, and then lastly, here's now we're going to remove this one, and we're going to fit it to the remaining 3. This is the fit that we get on the remaining 3. We throw the validation point back in, and we say how well did it predict? How far off was it? And we take the squared error and we sum that up. Okay, and so the total squared error, if I add all of those things up, ends up being 5.306. And because I had 4 data points, my mean squared error is going to be 5.306 divided by 4, and I get a mean squared error of 1.326. Is that okay? So that's cross-validation for these 4 data points. Okay, so we have a data set of 4, leave one out, we just leave one of these out at a time, and we fit the model to the remaining 3. And we just say, how well does that model that was fit on the remaining data points predict the one that was missing? And we keep track of that to get our total squared error, or mean squared error. Is this okay? All right. And so so we did it manually, and we found the mean squared error this way, and we got 1.326. In library boot, R has a function called cv.glm, okay, cross-validation for generalized linear model. So, GLM is basically the same as an LM, but you can also fit, logistic regressions and stuff like that. So here I just do, x by t, and this is on all the data, okay? So for this, you fit the entire data set. And if you do cv.glm, it will do leave one out cross-validation, and it stores its value right here, and we can see that R calculates the value to be exactly the same that we got, okay? And kind of the same process. So this is leave one out cross-validation. Are we okay here? Okay. So k-fold, so leave one out cross-validation has a few major drawbacks, right? One of them is that if we've got a lot of data points, the cross-validation requires you to fit n models, okay? Because each observation gets a turn at being the validation point, and so you're going to have to fit a model to everything else, and you're going to have to fit a total of n different models. So this is going to be very computationally expensive if you have, a data set of, of moderate size or more, okay? And then another thing is that the resulting models, because like the first iteration, you're keeping everything except maybe the last data point, and then the second iteration, you're keeping everything except maybe the second to last data point. The model that the first iteration produces and the model that the second iteration produces will look almost exactly the same, okay? Especially if you've got a large data set. All right, and so your coefficient estimates end up being very, very, very highly correlated to each other, and that results in some other issues, and you can end up actually overfitting the training data as well. Okay, and so one way to avoid this is using k-fold cross-validation. Okay, And k-fold cross-validation will take your entire data set, and rather than saying one observation is the validation point, you're going to maybe take your entire data set, split it into like 5 chunks or 5 blocks, k of these blocks, and each block gets a turn at being the validation set. Okay, so so generally you'll kind of shuffle these things. You'll shuffle all shuffle the observations and select a chunk of you know, of however many at a time. The remaining chunks serve as the training, and one block serves as the validation set. So if we did 4-fold cross-validation, we would take all of our observations, split them into, you know, 4 approximately equal sizes, and you would have the remaining 3 serve as the training data, and then you would validate it against this block. Okay, and you would go through and you would do this for each of the blocks that you've produced. Okay, so if you've done if you have 4-fold cross-validation, you only have to run 4 different models. Okay, versus in our original data set, we had 28 observations, so leave one out, cross-validation required 28 different models to be fit. Here I only have to fit 4 different models. Okay, so that's going to save us some computation time as well. Okay, and so let's take a look at the Olympic data again. So no longer a toy data set. We've got 28 observations. Okay. And here's just kind of the first 8 of these observations, the time, the year, and so on and so forth. And this is what it looks like. And so to do 4-fold cross-validation, I'm going to just shuffle the values 1 through 28. Okay? So index is all 28 numbers, but shuffled. And then I'm going to break those up into 4 sets: set A, set B, set C, and set D. So I'm going to take kind of, once I've shuffled all 28 values, I'm going to take the first 7, throw them into set A, take the next 7, 8 through 14, throw them into set B, and the next 7, and then the last 7 get thrown into set C and D. Okay? And so the different sets that I have, I'll throw into a list called set A, a list consisting of the 4 different sets that I've created. Okay, here's a little bit of code for kind of just a more generalized way to create these index sets. You don't have to worry about this, but you can use some floor division and you know, figure out where the start and the end points should be. But basically, I've taken all 28, I've shuffled them, and I've thrown, you know, 7 into A. So all 28 points are accounted for here, but they're all kind of shuffled up. Yes.
Is there a way of determining
how many number of folds to use is a tricky question, and I don't have a good answer for it. Okay, you know, 5 and 10 are probably common choices, but I think that's because we have 5 fingers on our hands. So I don't. These are just numbers that we like because they're familiar to us. But yeah, I don't know if they're a good thing. I used 4 because 28 divides by 4 evenly, and so I picked that. But somebody could have said 7, and that's probably fine as well. And then what I'm going to do is I'm setting up some vectors to store the results. We might have to wait for the results of this, but I just kind of, maybe I'll just introduce a little bit of the code, okay? And so basically, I'm doing this for I in 1 through 4. That's because I've got 4 different validation sets, okay? So for each validation set, I'm going to go through and I'm going to pull out that index, and those will be my validation indices. And my training X, I'm going to do everything in our original data minus the validation index, okay? So that's going to be my training data. And then the validation will be everything in my data that has the validation index. Okay, so again, V index is going to be one of these sets that I've created here, saying that, you know, observations 5, 10, 15, and 7, and whatever form our validation set. So we split our data into the training training X, training T, validation X, and validation T, okay? And then I put those together in a data frame to create our training data, and I put the validation data to create our validation data, right? So I put those into a data frame. And then I fit a model using the training data, and I have it create T hat values by taking that model and asking R to predict on the validation data. So I use the training data to create the model, and once I have that model, I use the predict function to make predictions for the validation data. And then I compare the validation actual value versus what I predicted, the T hat. Okay, I'm going to compare those, I'm going to square that and sum it. Okay, so we're going to get the sum of squared errors there. Okay, and that's just for model 1 where I fit LM to this. And this, I just expand this, basically copying the code, and I'm fitting 6 different models: a linear model, a quadratic, polynomial order 3, order 4, order 5, and order 8. So for each of these, I'm fitting a different model, but I'm doing the same thing. Fit the model, ask the model. Once I have that model, I ask that model to make predictions on the validation data, and then I compare the actual values versus the predictions, and I square those errors. Okay. We'll probably have to wait till Monday to get to see kind of the results of this, and we'll further talk about this. Okay, we'll see you guys. Hope to see you at Data Fest, and we'll see you there.